Good morning, everyone. My name is Khan, and I'm here to discuss a fascinating material, Kevlar. Kevlar is a composite fiber that was first developed in the 1960s and has since made a significant impact on the world. Throughout my presentation, I'll be explaining the science behind Kevlar and exploring its various applications in many industries. Without further ado, let's begin. So, what is Kevlar and what do we care about it? Kevlar is a synthetic material that is composed of polyparaphenylene terephthalamide, a type of aramid fiber. This fiber is known for its impressive strength with a tensile strength up to 6 times greater than A36 steel. In addition, Kevlar is also heat resistant and can withstand thermal hazards up to 800 degrees Fahrenheit. It was invented by Stephanie Kwolek and first introduced by DuPont in the 1960s. In 1964, Stephanie Kolek, who was a chemist at DuPont, was trying to develop a new material for use in tires. During her experiments, the polymer she had been working with formed liquid crystal in solution. This was a very unique thing to polymers at the time. The solution was described as cloudy upon being stirred, had low viscosity, and was usually thrown away. Despite this, she decided to try spinning the solution into fibers anyway, and she was amazed by the resulting fiber strength at the end. This material later became known as Kevlar 29 or K29. To put Kevlar's strength in context, let's compare it with other materials. Here I've collected data on the use strength, ultimate tensile strength, and Young's modulus of steel, titanium, diamond, and Kevlar. As you can see, Kevlar has a tensile strength of around 3,700 megapascal, which is higher than diamond by 1,000 megapascal. It is also 6 times stronger than steel and around 3 times stronger than titanium. In terms of stiffness, let's look at the Young's modulus. Kevlar is relatively flexible compared to other materials because, as we can see here, the Young's modulus is relatively low compared to steel and diamond. This makes sense because Kevlar was originally developed for tires, which require a certain level of flexibility. To explain Kevlar's properties, let's look at its molecular structure. Here I have with me a 3D model of a Kevlar's monomer. As you can see, the light blue atoms are the hydrogen, the dark blue atoms are the nitrogen, the red ones are carbon, and then the orange ones are oxygen. One monomer of Kevlar is made up of 2 aromatic rings connected by 1 peptide bond. A peptide bond is a covalent bond between 1 nitrogen atom and 1 carbonyl group. The high strength of this covalent bond significantly contributes to the high tensile strength of the polymer structure as a whole. Kevlar overall polymer structure is made up of long parallel chains of molecules held together by hydrogen bondings and aromatic stacking. The chain aligns to form sheets that are stacked to form fibers, and this unique structure gives Kevlar its exceptional strength and stiffness, as well as resistance to wear, tear, and thermal degradation. When monomers are aligned together, the amide groups have a partial positive charge on the hydrogen atom, but are attracted to the partial negative charge on the oxygen atom of the carbonyl groups. This attraction leads to the formation of strong hydrogen bondings that hold the Kevlar fibers together. Aromatic stacking, also known as pi-pi stacking, is another aspect of Kevlar's molecular structure. The parallel chains of Kevlar contain alternating rings of carbon atoms, which can stack on top of each other and create strong pi-pi bonds that hold the structure together. The stacked aromatic rings provide additional stability to the polymer, allowing it to distribute stress evenly along the molecule and making it less likely to deform or break under stress. Kevlar is well known for its use in protective gear such as body armor, helmets, gloves, and even shoes. In the automotive industry, the material is used in tire belts, brake pads, and hoses due to its high strength and resistance to heat and friction. Kevlar is also useful in the aerospace industry. It is used in aircraft components such as engine covers due to its thermal stability and resistance to fatigue and impact. Lastly, Kevlar is even used in the music industry, specifically for drums and string instruments such as guitars and violins. Now, we know that Kevlar is used to manufacture body armor. But can Kevlar really stop a bullet? Let's perform a short calculation on a 9mm Luger bullet to find out. Please note that this is only a preliminary calculation, so it might not be correct, but it will give us a general idea of whether Kevlar can be bulletproof or not. So, we have the ultimate tensile strength of Kevlar is 3757 megapascal, which is 3.757 10 to the 9 pascal. The cross-sectional area of a 9mm bullet is pi squared over 4, which ends up being around 6.4 10 to the negative 5 meters squared. Force F failure, or F max, would be calculated using the following formula. Delta is equal to F over A, so F is equal to delta multiplied by A, resulting in a force of 2.39 10 to the 5 Newton. For a 9mm Luger bullet, the velocity of the bullet at the end of the barrel is 352 meters per second. The length of the barrel, or the distance that the bullet travels, is 0.127 meter, and the mass of the bullet is around 8 grams, or 0.008 kilograms. The acceleration of the bullet can be calculated using this formula back in Physics 1. So V final square minus V initial square is equal to 2 times the acceleration of the bullet times the distance that the bullet travels. The acceleration ends up being 4.878 10 to the 5 meter per second square. The force at impact of this bullet would be F is equal to ma, which equals 3,900 newtons, so around 4,000 newtons. If we compare this result with Kevlar's force at failure, which is 2.4 10 to the 5, we can see that Kevlar body armor is, of course, effective at stopping a 9mm bullet, theoretically. However, we also know that body armor is not completely bulletproof, and in fact, even the thickest layers of Kevlar can be penetrated by high-power rifle rounds or armor-piercing bullets. So can Kevlar stop a 9mm bullet? Probably, but can it stop all kinds of bullets? Probably not. In conclusion, Kevlar fibers have a high tensile strength of around 3757 megapascal and a Young's modulus of 131 gigapascal. The reason is because Kevlar's molecular structure is tightly held together by covalent bonding, hydrogen bonding, and aromatic stacking. Kevlar is widely used in the manufacture of protective gear as well as in a variety of industrial and aviation applications. Although no body armor is completely bulletproof, Kevlar body armor is highly effective at stopping most small arms fire. This is the end of my presentation. Thank you so much for listening.